is blocking or tiling. So matrix multiplication is extremely important term. So in both in convolution layer or FC layer, matrix either matrix multiplication or matrix vector multiplication is performed. So I hope everybody understand how a matrix multiplication is done. So what we do, we take one row, we multiply it with one column. Then we take this row, multiply it with second column, that becomes this element. Then we take this row, multiply it with the first column, that becomes this element. Then we take this row, we multiply it with this column, that becomes the final element. In this way, our 2 into 3, this is 2 into 3 matrix, this is 3 into 2 matrix. So when we multiply 2 into 3 matrix with the 3 into 2 matrix, we get the 2 into 2 element. And the computation of one element is shown here with this shading. So I hope everybody knows what is matrix multiplication. Now, suppose we have matrices A, B, and which we multiply, we get the answer D. Okay. So till this point, I hope nobody should have any confusion or question. This is a straightforward matrix multiplication. Now, we do a very nice trick which makes our visualization very easy. I throw this D up. Okay. I push it up. I push it up. And I push this A left. Okay. These are the two things I do. So I push, sorry, not the A matrix. I push this D here. This A will remain at its own place, but D will come here. So let us show these matrices in a slightly different way. Let us push B upwards and D towards the left. So how it will look. Okay. Is it clear? We pushed B up and we pushed D left. Now matrix multiplication becomes very, very easy to visualize. How? Because one row of A and one column of B, they are generating one element of D. Now it becomes very, very easy to visualize, right? So before, if you don't see it, it becomes very, very confusing. Why are we multiplying one row with column and that is generating one element? But if you see like this, you throw one line from here, you throw one line from here, they mix at one, they intersect. That point is the element that you are generating. So is it clear to everyone how we are doing matrix multiplication? Okay, how we have done till so far? Okay, very nice. Now, similarly, you move it you move to the next column. Okay, so then you generate the next element. Next column, and finally you come here. You generate the final element. Similarly, you can go to next. Now you take another row. You generate further columns. When you take further columns from the another matrix, and you generate another further elements. Finally, you take this row and this whole column. Then you generate this element. Now, so this was naive method, right? We are doing matrix multiplication, but this is the naive method. Now, what we can do tiled matrix multiplication. We can use tiling or blocking. So what we do, we take, instead of taking one whole row and one column, let us take one tile. This is one tile, which is 2 into 3 tile, and this is 3 into 4 tile. Okay, this is 3 into 4 tile, this is 2 into 3 tile. So this is 2 into 3 tiles. So as you know in matrix multiplication, the second number here and the first number here, they should match. They should be equal. Only then you can multiply. So we have this A into B that is coming here. And now you can see this, the shading I have done is purposefully, it is light shading. That means if you just multiply this A with B, your answer D is not complete. You need to do more multiplications. Then I take this A and this B. Now you can see this is more darker. Then I take this A and B, this is darker. And when I take this A and B, it is more darker. That means finally this answer is complete. Okay. So here I have taken 4 tiles from A, 4 tiles from B. I have multiplied this tile with that tile, this tile with that tile, this tile with that tile, and added them. That has given me So what that means, whatever is happening at the level of the whole matrix, same thing is getting happened. Same thing is happening at the level of submatrix or tile. A tile is just a submatrix. So I'm multiplying some matrices, and by adding their partial sums, I'm generating the whole matrix multiplication. Okay. That's all. That's all matrix. That's all matrix this tiling is. Now we'll see how do we do. How do we do tiling of the matrix transpose operation? And then we'll see. Then we'll see how do we do tiling of the matrix multiplication operation. Okay, so first we will see the cache blocking of matrix transpose operation. Transpose is much easier operation compared to matrix multiplication operation. So that's why I'm first illustrating transpose operation, and after transpose operation, I will show the multiplication operation. Now, blocking is also called tiling, but blocking is not same as cache block. These two are different concepts. So here is a simple code for showing the matrix transpose operation. Okay, so here everybody knows what is transpose. We take Aij and store it the Ji. So in Microsoft Excel, you can take a matrix, copy it somewhere else, and you can, instead of pasting in a normal way, you can paste as a transpose. So that's also possible. So here, suppose both input and output matrices are stored in row major order. So I have already explained what is row major order. In the above code, we are accessing multiple arrays such that some arrays are accessed by rows, some by columns. So we are accessing this by row and this by column. You can easily see that we are accessing Aij with we are accessing row wise, and we are accessing Bji with column wise. Now, simply changing the loop order will not help here. Right? If you remember in the previous example, which I showed last time, we did loop interchange. Okay, but here loop interchange will not help. Why? Because even if for example, if you take this loop here and this loop here, now your accesses for B are improved, but the accesses for A, they are not. There you have more cache misses. Here you have less cache misses, and there for A you have more cache misses. So that means in one loop order you are benefiting A, in another loop order you are benefiting B. But there is no loop order where you benefit both A and B. Okay, so that's the idea. Okay, now let us assume that each element is 1 byte. That means here A, suppose they are car, right? CHAR, car. So in C, a car takes 1 byte. Now let n equals to 4. Okay, so this n, this loop index, that is 4. So we are accessing 16 elements of A. That means A is a 4 cross 4 matrix. So A has 16 elements, and B has also 16 elements. Okay, till this point it is clear. A has 16 elements, B has 16 elements. There is no reuse of either A or B. Each element is accessed only once. Is it fine? Each element is accessed only once, because Aij, for any ij value, we are accessing it only once. If cache block size is just 1 byte, there will be 32 misses. Now let us see. So this point should be clear to everybody. How, if the block size is 1 byte, there will be 32 misses. Let us see how. Because why? Because see, we are accessing 16 elements of A, and we are accessing 16 elements of B. Right? We are accessing total of 32 elements we are accessing. And for each element, we will have a miss because those elements were not there in the cache. So those elements will lead to a miss. So if a cache block size is 1 byte, then we will have 32 misses. Now, one more thing is there. If you know at least a little bit about cache, you can somewhat understand, although actually you don't need a lot of understanding of the cache. But if you don't know anything about the cache, I request you see my lecture video on caches from ECN 204. Even this year I have already discussed it. Just today I discussed and last week I discussed. So if you do not know anything about cache, you can probably see that half-an-hour video. But here I don't think you need to understand it, the whole cache fully. But if you're feeling not very confident, you can see one of the videos. You please send me an email. I will tell you the exact video. Okay. Now, if the cache block size is just 1 byte, all the 32 accesses will lead to a miss. Okay. Now, if the cache block size is increased from that means instead of 1 byte, suppose we were to use 2 bytes or 4 bytes, then there is a possibility of reducing the cache misses. Actually, today itself I discussed this idea of block. If you want, I can refer to you that video. Okay. Now, suppose n equals to 4. Okay, that's already there. Now, suppose instead of 1 byte, let us use a cache block size of 2 bytes. And each element is anyway 1 byte, that's already given. And we have an 8 element fully associative cache. Okay, we just have one cache which has 8 elements. So first, I will show you how many misses happen if we do not use cache blocking. Somehow we store A in row major order and B in column major order. Although generally it's not possible that we will store one matrix in row major, another matrix in column major order, but somehow we assume, somehow we have saved B in column major order and A in row major order. Then let us see how many of those 32 accesses lead to a miss. See, we have a total of 32 accesses. Some of them can hit, some of them can miss. So let us see how many misses happen if we use this organization. So before I show in detail, let us see what all I am going to show. I will show first case where we don't use cache blocking. I store A in row major order, B in column major order. Then I will show you here both of them in row major order and without cache blocking. And finally, I will show you with cache blocking. That means let us use both of them in row major, but can we use cache blocking? And then let us see how many cache misses happen. Okay, now let us start from here. So this is the first case. This is the case number 1, where I have A in row major order, B in column major order, and there is no cache blocking. So here, this is just the definition here, just as a reminder that A is stored in row major order, B is somehow stored in column major order. So this is the storage pattern that we will use. Okay, so this is our matrix B. This is our matrix A. So this is the logical representation, and this is the physical storage. How it is stored in the memory. And this is our code. We will execute this code. This is the matrix transpose code that we will execute. And because A is always in the row major order, so that I have not written here, I've just written that we are not using cache blocking, and B is stored in column major order. And we will show the indices as ij, right? So this is the ij. So now suppose first you do first iteration of this for loop. So initially A is ij is 0, 0, and here also we have 0, 0. Okay, we have this 0, 0. So because our block size is 2 bytes, so we will access one block each from A and one from B. And because our block size is 2 byte, that means that block will have 2 elements. Okay, so once we access A00, as you can see, once we access A00, I will also access A01. And once I access B00, I also access B10. Okay, this is B10, it is not B01. For A, it was 01. For B, it is 10. Okay, so that means B, it is 10. I've written here. We access one block each from A and B. So accessing this block led to a miss, and accessing this block led to a miss. So we had 2 misses. Is it clear till now? If you have any question, please ask, because after this it will get. If you understand till this point, the rest of the presentation is very easy. How do we decide cache miss in a hit?
Excuse me, sir.
Yes.
So what are we referring as a miss?
Miss means, okay, that's a good point. Suppose you go to the library Okay, you ask for a book, and if the book is not there in the library, you call it a miss. That means you don't know what is cache. You're asking this means you don't know what is a cache. I actually definitely recommend all students to go through that cache video. I will send that link today after the class. It looks to me that most students don't know about the cache. So you please see that video. I mean, it's just less than 2 hours video, the whole thing. So maybe one and a half hours. Okay, so if you go to the library, you find a book, that's called a hit. If you don't find the book, it's called a miss. Right. So if you see, if you can find some book in the library, well and good, right? Because it saves your time. If it is not there in the library, they will have to ask it for. They have to issue a purchase order that will take 2-3 months with all the paperwork. So you don't want that, right? So that's the idea. Okay, so now let us do next iteration. So next iteration, what is the value of ij? Can anybody tell me? I have done first iteration. Now second part is what will be the value of ing?
0 and 1.
Very nice. Yeah. So I will be 0 and j will be 1. So this will become 1 and j will be 1. Okay. So now I now in this second iteration, I need B10 as I've written here, B10 and A01. Okay, A01. So can anybody tell me, are they in my cache? These two elements, I need A01 and B10. So are they already there in the cache or do I need to fetch them from memory? See the cache, whether they are already stored in the cache.
Yes, sir, they are.
Yeah, so as you can see, A01 is already there. At the time of fetching A00, I also fetched A01. So that is already there. Similarly, at the time of fetching B00, I also fetched B10 there. That is also there. So both lead to cache hits. Accessing A01 and B10, both are cache hits. So 2 hits, right? We made 2 accesses, both of them hit. Okay, now I go to further iteration. So now what is the value of j? 2, right? I remains 0 and j has now moved from 0, 1 and 2. So this is 0, 2 and this is 2, 0. However, neither A02 is there nor B20 is there. So as you can see here, neither B20 is there nor A02 is there. So I need to fetch them. Okay, I need to fetch A02. So I will fetch A02. So when I fetch A02, what all will also come? What will also come if I fetch A02?
03.
A03.
Yeah, so when I fetch A02, A03 will also come. And I also need B20. Right? I also need B20. So I fetch B20. So what all will also come?
30.
Yeah, B30 will also. Okay, it's very clear. So now, when I fetch B20, then B30 will also come. And when I fetch A02, then A03 will also come. But at least both of these were misses, so these are 2 misses. Okay, so both the 2 accesses, they lead to a miss. Now finally, I have iteration number 4. Now the value of j has reached 3, so I need 0, 3. And here for b, I need 3, 0. Okay, 3, 0 and 0, 3. So can anybody tell me whether they are already available in the cache or do we need to fetch them? So see here, whether A03 is there or not.
Yes, sir. Yes, sir.
And B30, is it there?
Yes.
Okay, so both are
Yes,
there,
sir.
so they will both lead to hits. So here I have 2 hits. Okay, so now you can see here, for one particular value of I have already discussed all the 4 possible values of j, and they are all there in the cache. Okay, and out of those 8 accesses, right, for the in these 4 iterations, I made 8 accesses. Out of those 8 accesses, how many were hits, how many were misses? Please tell me.
Half hits and half misses.
Very nice. So out of the 8 accesses, 4 were hits, 4 were misses. Now I can go to the next value of I. So now I will become 1. Till now I was 0, but now I has become 1. So now I need A10 and B01. Okay, because I is equal to 1 and J equals to 0. So I need A10 and B01. So both are miss. So I will have to fetch them, and whatever were the two oldest blocks, I will replace them from the cache. Okay, I remove two oldest blocks from the cache. So I will remove them now. So these two blocks are the oldest. I throw them away, and I bring A10. With that A11 also comes, as you can see here. When I fetch A01, then A11 also comes. Okay. Similarly, when I fetch B01, then B11 also comes. When I fetch B01, then B11 also comes. So like this. So our observation was in 4 iterations, we get 4 hits and 4 misses. Out of 4 accesses to A, 2 are misses, same for B. And if you continue like this, for the whole matrix transpose, out of the 32 accesses, 16 misses will happen and 16 hits will also happen. Okay, 16 misses will happen and 16 hits will also happen. So total out of 32, 16 misses and 16 hits. So this was the summary. Now let us go to another case where we have no cache blocking. Now A is stored in row major order, B is also stored in row major order. So compared to previous case, here B was in column major order. Now in this case, I store B in row major order itself, and then see what is the difference. Here, now please remember, here it is, I've explicitly shown it in the row major order. A is same, row major order. Previously, this was column major. Now here, B is stored in the row major order. So if anybody has any questions till this point? Okay, very good. Now, this remains same, this remains same, this remains same. Till this point also it remains same. I need A00 and B00. However, when I fetch B00, another data element which comes with it is B01. As you can see here, when I fetch B00, I also fetch B01. Whereas in the previous case, when I fetch B00, I get B10. And now I'm getting B01. This is the main difference. When I fetch B00, now I'm getting B01 also. So that I store here. So both these accesses lead to a miss. Now my I value is still 0 and J value has become 1. Okay, so this has become, so I need B10 and A0. So out of these two, so now tell me which of them will lead to a hit, which of them will lead to a miss. I need A01 and I need B10. Please tell me which of them will lead to a hit, which of them will lead to a miss.
A01 is
A01.
A01 hit.
B10 is miss.
B10, because as you can see, B10 is not there, right? So now when I fetch B10, what all will come? Please tell me.
B11.
Yeah, when I fetch B10, then B11 will also come. So that I have shown here. So out of these two hit, we made two accesses. One was this, one was this. Out of them, how many are hit? How many are missed?
1 hit, 1 miss.
Hit,
Okay, so
one
that I've
miss.
shown 1 hit, 1 miss. Okay, so this is the summary till now. Now let us go forward. Now I need A02 and B20 because J will move to 2. J will become 2. Both of them are misses, as you can see. Right? Neither in this cache, I neither have A02, neither I have B20. So both of them will miss. So I have to patch them, but there is only one free space. There is only one free space. One space for just one block is there. So I will have to remove the oldest block. Suppose I remove this block. Or suppose I remove this block. Let this block be there. Suppose I remove this block. Whichever is the oldest block we remove. So we remove B00, B11 block. Or we could have removed this block. That doesn't need it there. So now both of them are missed. So here I have shown 2 misses. Okay. Now, for finally, the value of J becomes 3. So now I need A03 and B30. Out of them, which one will lead to a hit? Please see whether A03 is there in the cache. Tell me whether A03 is there in the cache.
Yes, sir.
And B30 is not there, right? So out of them, one will lead to a hit, but another will lead to a miss. So fetch it and remove that block, which is the oldest. So this block is the oldest. So we'll remove it. We'll fetch B30. And when we fetch B30, what all comes? When I fetch B30, what comes?
B31.
B31.
Yeah. So now we can see, because we have stored B in row major order, we are not accessing nearby elements. We first accessed this, then we access this, then we access this, then we access this. So we are not fetching nearby, right? We did not fetch this, we did not fetch this, we did not fetch this, we did not fetch this. So out of those 8, in these 4 iterations, out of the 8 accesses, we had only two hits, right? This was 1 hit for A, this is another hit for A. All others are misses. That means 6 misses and 2 hits. Especially for B, we did not have any hit. All accesses to B are misses. And out of 4 accesses to A, 2 are misses. And we can continue this for the next 4 iterations also. Finally, we'll find out that out of 32 accesses, 24 are misses and 8 are hits. So can you tell me these 8 hits, will they be to A or to B or to both? I have 8 hits. Will they be to A?
All
Yes.
belongs to A.
Yeah, all belong to A. Yeah, only for A we will have hits. For B we will not have any hits. That's what we said here. That simply doing loop interchange will not help. So in this particular with this organization, suppose if both are in row major order, I have lot of hits for A. I don't have any hits for B. If I change the loop order, then I have lot of hits for B. I will not have any hits for A. That's what I have shown here. Okay, so now let us see why things are happening the way it's happening. So suppose this is our access pattern Aij. We are accessing A like this, and we are accessing B in this manner because it's a transpose operation after all. We're accessing A in a row major order. We are accessing B in a column major order. By storing A in row major order and B in column major order, we can exploit the reuse. That's what we show in case number 1. But actually, it's not possible to store one matrix in one order and another matrix in column major order because it will involve a lot of rearrangement. So now let us see, can we do something about it? So if you observe, we had fetched B00, B1 block earlier, but later we evicted it. As you can see here, we patched B00 and B1. We patched it earlier, and later we evicted it. When did we evict it? Here we evicted it, right? And now we are again fetching it, isn't it? We brought it. Suppose your bag can only hold 2 books. So you fetch computer architecture and computer networks. Later, you need to fetch another book. So you have to remove one book. Suppose you remove the architecture. You don't like architecture. You remove it. So you bring suppose circuits and systems. Then after some time, you will realize, okay, I need computer architecture. Then you will again fetch computer architecture book. So that's what is happening here. We unnecessarily evicted it, even though we had to use it in future, but we evicted it. So we had B00, B1, B01. Okay, so that was the case. Now we are fetching it again. So how to avoid this waste? We will use blocking. So the difference is that if you change the layout of B from row major to column major, it will require changes in the hardware because you have to change the way the B matrix is stored. For example, here, this is the way B matrix is stored in the row major order, and this is the way B matrix is stored in the column major order. So if you want to change from row major to column major, I will have to do a lot of changes. Move this element here, move that element there. That will be a lot of changes. Instead of doing that, let us do the changes in the software. That means I will just write the code differently. Okay, I will not do any changes in the hardware. Let the data be stored in whatever way it is stored. I will just write my code differently so that I can still have very better code, very good performance. So here, remember, I'm allowing, okay, A and B, let them be stored in row major order. I will just write my code differently. That is called cache blocking. So I will do cache blocking. So let us see how do we do that cache blocking. Okay, so here, unfortunately, our code becomes slightly complicated, and here it is just, transpose operation, which is still simple, but as you go to very nested level, nested for loops, the code will start becoming very complex. But the principle is simple. The principle is, see, earlier we had two for loops. Now we have changed to 4, because each of the for loop we have done uh, tiling, or we have done blocking of that for loop. So here you can see that we increment this u by q, and this further we are having w, which goes up to q. So this q is called blocking factor. So we are having just one block. If you remember my previous presentation, which was from NVIDIA, I take one submatrix from A, one submatrix from B, and that's what I'm doing here. Each time you can see just this part. If you forget the upper part, this 2 levels of for loops, they are multiplying one submatrix of A with one submatrix of B, or one tile of A with one tile of B. And if you now take all the four for loops, they are doing the multiplication of the entire matrix. Of course, this is a transpose operation. So transpose is not same as matrix multiplication, but the key ideas are same. Okay, so here this is the matrix B, this is the matrix A, and I have written this for nested 4 levels loop, 4 levels of loop. Okay, so let us show their indexes as UVWX. So this was UVWX, and Q, which is a blocking factor, let it be 2. So in the first iteration, this UVWX, let us see their values are 0, 0, 0, 0. Okay, their values are 0, 0, 0. So now, as previous case, this is the A00 and this is the B00. Okay. So we access one block each from A and B. So we access this from A and this from B. And with A and B, we will also get A01 and B01. And we have 2 misses. Now I have the lowest level loop, which is X. So this X will increment, right? This X will increase to 1. So now I need what? I need 0 plus W is what? So sorry, U plus W. So U plus W is still 0, and V plus X is 1. And V plus X is 1, U plus W is still 0. So I need A01 and I need B10. Right? I need A01 and I need B10. Out of them, A01 is cache hit, which I've already shown before, and B10 is a cache miss. Okay, B10 is a cache miss. So because B10 is a cache miss, I need to fetch B10. With that also comes B11. And here I have 1 hit and 1 miss. All right. So now till this point, it is same as the second case. Now comes the difference. So this thing I have again copied here because we will need to see this. Now, as you can see, Q is 2. So once X becomes equal to 1, at next iteration it will become 2. So this iteration will stop. Now we again come back to this iteration. Now W will go from 0 to 1 and X will again become 0. Is it clear? This is the simple for loop. Now the innermost for loop has ended, right? And I will go to the second for loop. This for loop. I have to go to this for loop where the value of W will increase to 1, and finally when I enter this for loop, X will again become 0. Is it clear? How I got this value of iteration UVWX? Okay, I hope it is very clear. This is a simple for loop. Now, remember, so UVWX. So U is 0, B is 0, W is 1, X is 0. So I need B01. Similarly, I need A10. Okay, and out of them, let us see which of them is a cache hit. So B01, it's already there in the cache. As you can see here, B01 is already there in the cache. Right? And A10 is not there. Right? A10 is not there. Here. A10 is not there in the cache. So A10 will lead to a cache miss. So here you can see out of the two accesses, one hit and one miss. Okay, now in iteration 4, now W is also 1, X is also 1. Right? Because X goes from 0, 0 and 1. X goes up to 2, so that means 0 and 1. So I need now A11, B11 because V is 0, X is 1, W is 0. W is 1 and U is 0. So it will be B11. This 0 plus 1 is 1 and 0 plus 1 is 1. So I need B11 and its transpose A11. Both are hits. That is really good case. Because B11 is there, A11 is there. Isn't it? So I have two hits here. So in the first 4 iterations, we get 4 hits and 4 misses. So out of 4 accesses to A, 2 are misses, same for B. Okay. So is it clear to everyone? If no, please ask question. Okay, somebody is typing chat. No, I can't do that before the class. I can do it after the class. I can do it after the class because so in these 4 iterations, we get 4 hits and 4 misses. Is it clear, everyone? Okay, so now if you continue like this, if you have any question, please ask because this presentation is going to end. Now for the whole matrix transpose operation, we will get 16 misses and 16 hits. That means half of the accesses will miss, half of them will hit. This is what is happening. Previous case, when we are doing A, we are iterating over A in row major, B in column major order. When we do, so in this case, actually not all of them was fitting in the cache. But when we do blocking, so we are now operating, we are not, for A, we are not going till the end of the row. We are just going in till half of the row, or maybe one fourth of the row. And then we are again coming to the next row. So like this. And here also we are going just one, this is one tile, this is one tile. So because I'm operating only on tiles, that tile pattern can fit into the cache. The whole accesses, they don't fit in the cache, but if I just access tile by tile, that can fit in the cache. So there, this plus this is less than the cache size. That's why I get more hits. Okay, so I have just changed. The way B is stored in the memory, I have not changed that, but I am iterating over B in a different manner. I am iterating over A in a different manner. That is cache blocking. Here you can see I just changed the code. So this is the new code, right? I will have to write the software differently without changing the hardware. This is the summary. If I have no cache blocking and if I store B in column major order, then I have 16 misses, which is best. Now, if I have no cache blocking, but B is stored in row major order, then I get 24 cache misses, which is not very good. It's bad design. But if I use cache blocking and store B in row major order, I get 16 misses. For this example, for a different example, this could be different. Okay, so this is the benefit of cache tiling or cache blocking.